So anyway, I would like to wish happy birthday to Noga. It was not so easy to find out what I should talk about today. There's another picture, and because this is really an embarrassment of riches, where you can, if you want to pick some result, maybe of Noga, and then try to talk about this, and so I thought of extreme graphs, which was our, I think we both learned it from Uncle Paul, this beautiful subject, or about the Shannon capacity, maybe about the strong regularity lemma, property testing, combinatorial Nullstellensatz, and the other matrices. Optimization. Now here I was a little bit, first I wanted to talk about this topic because Noga is very well known for optimizing things. For example, there is this legend that at the institute in Princeton that Noga very carefully optimized the way between his apartment and the institute. He determined that on foot it takes 3 minutes. By car it takes 2.5, so he was using his car to get there. So with this, anyway, at the end I decided maybe not to talk about optimization, and then I got to the idea of eigenvalues, and I decided to talk about eigenvalues of graphs. So here is, if you have a graph, you can construct its Laplacian. It's a matrix, and that's the first point where, from my laptop, the M would be 3 dots, but unfortunately they don't come out all right. So anyway, so ignore the M's. So this is a matrix. Rows and columns are indexed by the vertices of a graph. You put a -1 if the two positions, the column and the row position, are adjacent, 0 otherwise, and in the diagonal to put the degrees of the nodes. This is a positive semi-definite matrix. Least eigenvalue is 0, because if you apply it to the all one vector, you get a 0 vector. So this is the Laplacian, and the Laplacian is a very important matrix associated with any graph. So it has certain eigenvalues. The least of them, lambda 1, is 0. And now the second one is positive if and only if the graph is connected. It's an easy consequence of the Perron-Frobenius theory. And so the question is, what can we say more about the difference between these two, the eigenvalue gap, which is, of course, famous in many other parts of mathematics. And there's a rather old result by now, I'm afraid to say, by Allon and Millman, and then in the other direction by Allon, proving that I won't formulate it exactly, the gap between lambda 1 and lambda 2, if there is a gap between lambda 1 and lambda 2, a constant gap, then this is equivalent to the graph being an expander graph. Of course, I will come back to this later. Let's now go on and introduce some more notation. So given we have a simple graph on n vertices, a G may... Okay, so the upside down exclamation mark is a little bit unusual notation for the set of real numbers. So I will, I apologize for this. So we have a G matrix, which just means that it's a real matrix and symmetric, and the entries corresponding to non-adjacent positions are 0. So it has values for the edges and values for the nodes on the diagram. And it's well signed if the off-diagonal entries are negative. And we call it really good if it's well signed and it has exactly one negative eigenvalue. And you will see why this condition is so interesting. To have exactly one negative eigenvalue. And we would like to understand, the solutions of the following situation. We want a product where n equals 0, where n is a G matrix and U is some other matrix, D by n matrix, where we assume that D is the rank of U, so the rows of U are independent, and it's also the co-rank of M, so the situation is tight, so the UN product can be just 0. We'll see many examples of why understanding this equation is interesting. One thing is that if you have the n, then you can reconstruct the u in a quite easy way. So you look at the null space of M, you take a basis in it, you write down as row vectors, and they will form U. So every row of U should be in the null space of M. M is symmetric, it's a G matrix. And then, however, we can read this U column by column, and therefore we assign a vector in RB to every node of the graph. So basically, by having such a situation, we can map the nodes of the graph into this space. And the question is this any interesting configuration geometrically? Does this configuration have any particular graph theoretical geometric meaning? We'll see that the answer is often yes. By the way, the null space representation is unique up to linear transformations. If you choose another basis in the null space, you will just apply a linear transformation in the D space, where you are representing the graph. So this is really something which, up to this linear transformation, is a property of the matrix M. So let's start with some examples of this situation. The first one is the following. It's a construction by rubber bands. So you take your graph, you take a cycle in your graph, and you fix these cycles to a convex polygon in the plane, the nodes of these cycles. And then you replace the other edges by rubber bands. And then you let this whole configuration find its equilibrium. And this way you get a picture, a particular drawing of the graph in the two-dimensional space. Now, there's a classical, this construction was first probably used by Todd, and he proved that if the graph is planar and sync-connected, which is a technical assumption needed here, then actually, so if, and then they will start with a face, so the starting polygon is the border of a face, then this construction will actually give you an embedding of the graph in the plane, meaning it doesn't produce any crossing edges. This is a very nice area, not so easy. And so this is the construction. Now, it's just a couple of nice pictures you get this way. It's a construction which is really used in graph drawing software quite often. So to analyze this, you look at the energy of this whole picture. Here, the Mij is the stress in the rubber band, or the strength of the rubber band. It only depends on the rubber band. It's a parameter associated with the rubber band. In this case, it's positive. And assume Hooke's law, which says that if you stretch the rubber band to length t, then the energy it will store is proportional to t squared. And then you sum it to parallel edges, so that's the total energy of the rubber bands. And the equilibrium condition is, if you take a gradient, as the sum of mij times uj minus ui is 0, where you sum over all, you fix a free node, I, and then you sum over all neighbors. So this means that the forces that act on that node sum to 0. And if you wish, you can introduce diagonal entries for which is the negative sum of the others. So just like in the Laplacian case, this makes the row sums equal to 0. And in that case, we can simply write this as sum of j, mij, uj equals 0. So it gives a solution of that very simple equation that we want to understand. And this matrix is called the stress matrix. Any matrix that satisfies these conditions will be interpretable as a stress, a matrix of stresses in a particular physical construction. Now, if they are supposed, for simplicity, that the outside faces a triangle, then of course, you can think of nailing the three nodes to the desk, but you can also think of replacing those edges by bars. So you form a rigid triangle by 3 bars, and then the rest will be rubber bands just like before. And then you get, it's a little bit different interpretation of the same picture. So these mij's are stresses, and then you can define for these bordering edges also stresses, so that the equilibrium condition will also hold at the 3 nail nodes, and then you don't need nails, because obviously if you have a rigid triangle, pull out the nails, it will not fly off, or nothing will happen. Stay in equilibrium. So of course these border mij's will have a different sign. Here is another construction of similar nature. You take a configuration which you build out of, there is a convex polygon which you make out of cables, and then you put in bars for some diagonals. You can think of the cables as rubber bands, so you have a rubber band around the picture, but then you will think of the bars, if you wish to change to this way of looking at it. They are sort of very strange rubber bands which push, anti-rubber bands which push the 2 points apart, and they push, if they go farther and farther, then they push stronger and stronger. So strange situation. So if you have this, then you can assume that there is some forces acting here that will produce equilibrium, and again you get a solution of the same system of equations. Now Connolly proved that it's a non-trivial theorem which says that this matrix of stresses acting in this picture, this matrix has corank 3, and it is positive semi-definite. Now, corank 3 is clear that it has at least 3, corank is at least 3, so it has at least 3 zeros, because the coordinate functions, equilibrium means that the coordinate functions are in its node space, and in addition, the whole one vector is in its node space, as the sum of the mij is 0. The whole sums are 0. So that it has corank 3 is clear. it's trickier to prove that it has corank exactly 3, and then also it's coming to eigenvalues that it is positive semi-definite. Now, I was kind of interested in this positive semi-definiteness is because if you look at the energy of the situation, just like before, except I put now a negative sign, doesn't matter, just more than then I can look at what happens if I perturb the points by a vector x. So each point is moved by a small little vector xi. Then just expanding the expression and using that u is an equilibrium, the original position is in equilibrium, you see that that the energy of the original is just increased by the energy of that would be assigned to these xi's. So if the matrix is positive semi-definite, this means that the energy is increasing, and that means that it's in a stable equilibrium. So this positive semi-definiteness corresponds to stability of this equilibrium. So, of course, if you have just any solution of our original equation with no space representation, we can always add, make the row sums of m to be equal 0 by adding an additional row and column. Okay, and also I can add an additional 0 rows to the views, and then I get another solution which can be interpreted as a stress matrix. So in this case, we can think of this differently. It's not that I replace the ordering 3 edges by bars, but then I put a new bar, a new point in the middle, and then I sort of put bars to the vertices. They will brace out the whole picture, and then you get again equilibrium. Now, let's, it is a construction in 3 dimensions of something similar. Let's look at a polytope and P, and I also will use the polar polytope P star. It is known that there is no stress on the edges of the polytope. That's a real classical theorem going back to 1822, that on the edges of the convex polygon, you cannot define a stress or equilibrium at each point. On the other hand, if you allow this brace, so you are allowing to putting a point inside the polytope and brace it from that, then on every polytope you can define a stress, and in fact in a canonical way, if you take a look at an edge of the polytope, then the edge is bordered by 2 faces. The 2 faces correspond to 2 vertices of the polar polytope, so there is a polar edge. Now, the 2 endpoints of the edge, the vectors pointing, I assume now that the origin is in the interior of the polytope. So the 2 points that that form the endpoints of this edge are both orthogonal to these 2 faces. So they are orthogonal to the difference of the polars. So the polar edge is orthogonal to both vectors that point to u and v, and therefore it's parallel to the cross product of those 2, and this defines a matrix with a coefficient m2b for this situation, and I call this the canonical base stress. So this way we define a matrix which gives a stress, gives a solution of our equation, and it turns out that this has one negative eigenvalue three zero eigenvalues, but again, it's easy to see that it has three because every coordinate function gives an eigenvector, gives a vector in the null space. But it's a little bit more difficult to see that it doesn't have four, and it's quite difficult to prove that it has exactly one negative eigenvalue. It's not difficult to see that it must have at least one negative eigenvalue, because the zero eigenvalue cannot be its smallest eigenvalue because of this argument that if it's a connected graph, then the smallest eigenvalue must have multiplicity 1, like Baron Frobenius, but that it has exactly one negative is I don't know a simple proof of that. So this gives a really good G matrix as we define those guys. Now, another, Colin de Verdier started to look at what I call now really good G matrices. Another way of looking at it is that you have a connected graph, and you look at the usual adjacency matrix, and you are interested in the multiplicity of the second largest. The largest eigenvalue has multiplicity 1, so what happens to the second largest? This is now, in terms of the adjacency matrix, now the Laplace. So you are interested in the second largest eigenvalue, not because the largest has multiplicity 1, so that's not interesting. Now, usually the second largest eigenvalue will also have multiplicity 1, so that's an uninteresting situation. But you can maximize over all weightings of the edges and the diagonal entries to make this multiplicity as large as you can. And essentially this is the number, the parameter that Colin de Verdier introduced. He added a non-degeneracy condition on weightings, which I will ignore for the purposes of this talk. So formally, we have a well-signed G matrix, which has exactly one negative eigenvalue, so it's a really good G matrix. This is actually just a normalization, so once you have a well-signed G matrix, you can always translate the diagonal to make the second smallest eigenvalue equal to 0, and then is the strong Arnold property, the non-degeneracy property, which is a very, very interesting property even from combinatorial point of view, but I really ignored it for. If you are for today, you can always replace it by, or usually you can replace it by some connectivity assumption about the graph. And then you look at the corank of this matrix and you want to ask how large this corank can be. So this parameter, you can introduce it in connection with every graph. So why is it interesting? Well, it's interesting because it has many nice properties. So first of all, it is minor monotone. So for the graph theorists, of course, this is a very important property. It says that it's if you delete or contract edges of a graph, then this can only decrease. And why is it an important property? For example, it implies by the results of Robertson and Seymour on graph minors that you can decide in polynomial time. So you can basically compute it in polynomial time as long as its value is a constant. By the way, this is one of those strange situations that you know you can compute it in polynomial time, but we don't really know how to compute it in polynomial time, because to get an algorithm, say to check whether mu is less than or equal to 5, so whether there exists such a really good matrix for a given given graph with core rank 5. To decide this, you would have to determine a list of excluded minors, and nobody knows what those excluded minors are. So this is a pure existence proof of an algorithm. It's a strange situation. It's known to be invariant under subdivision. It's also invariant under a more complicated transformation called delta Y transformation. So it has many nice properties. But even more important is how its special values relate to properties of a graph. Well, that most one if the graph is rather trivial, that's very important, not very interesting. But the second one is already interesting. Mu that most true if only if the graph is outer planar. Outer planar means that you can embed the graph in the plane so that all the vertices are on the infinite face. Basically a cycle with diagonals, and you may delete edges from the cycle. So it's part of a cycle with diagonals. Non-crossing diagonals. So mu G at most 3, this is even more surprising, if and only if G is planar. Colin Devaney proved this, and that made this fact made, of course, graph theorists interested in this parameter. He used some partial differential equations to prove this. The elementary proof was given by van der Horst. So this is this is already a very surprising connection. So you look at the multiplicity of an eigenvalue and relate it to planarity of the graph. So some very basic and topological type graph property. So van der Waals proof involves a lemma, and I would like to formulate this lemma because it's really quite interesting and again relates to lots of things. So suppose we look at a really good G native. So again, this is off-diagonal entries are negative or 0, and it has exactly one negative eigenvalue. And let's consider a vector in its null space, so belonging to the second smallest eigenvalue. And let's choose one for whose support is minimal. I mean, the null space typically has larger, interesting cases has larger dimension, so we can choose many vectors there. Let's choose one whose support is minimal. The non-zero elements by inclusion, its inclusion minimum. And then we split the graph into 3 parts, those where the value of this eigenvector is corresponding entity is positive, 0, or negative. And now it turns out, that's what the lemma says, that the positive support and the negative support span induce connected graphs. So the graphs on those set of nodes are connected. This is in fact a discrete version of Grant's nodal theorem for partial differential equations. But for graphs, it's a very useful observation. Fact, it's an interesting lemma, a very useful lemma. You can formulate it also in a geometric way. It says that if you look at the null space representation that goes with this X, with this for this matrix, so this embeds the graph in some dimensional space, and now you take a hyperplane to the origin. Then this hyperplane will cut the graph into 2 parts, which are both connected. And it turns out that there's some exceptional case, in which case it cuts it into more than 2 parts, but it's a very special situation. These are all lying in lower dimensional spaces, and the intersection is a co-dimension 2 subspace with the space and so on. So there is a well understood exceptional configuration. Now I'm showing you this picture because this property that if you take a hyperplane, it cuts it into 2 connected pieces, it should remind you of polyhedra. If you have a polyhedron and you cut it into 2 parts, then both parts are connected. And indeed, it will turn out that this has something to do with polyhedra, so like convex polyhedra. So let me, just to show how this lemma can be applied, argue that if you have such a matrix, so you have a planar, 3-connected planar graph, you have a really good matrix that goes with it, then it cannot have a 4-dimensional null space. Well, if it has a 4-dimensional null space, then you can take a vector in this null space, which is 0 on this is only visible on my screen. So I look at the 3 black nodes, and we take a vector on the nodes, which is 0 in the 3 black nodes. And then, because if it's 4-dimensional, then you can fix 3 of the coordinates and still get such a vector. And then if you have a positive support and a negative support, and the other values are 0. Now the graph is 3-connected, so there are 3 paths connecting the black nodes to the support. I don't know whether they go to the positive or negative part of the support, but if I follow them until the last point before the support, then just by the fact that it's in the null space, so if you so the value in that last point is 0, but it has a positive neighbor, and also has to have a negative neighbor, because and so all these 3 points have neighbors in both the positive and the negative support. Now you take another point and connect it outside of everything and connect it to the 3 black nodes, and you contract the positive and negative supports of single points, which you can do because they are connected by the lemma, and you get a case with 3, which you cannot have in a planar graph. So it's just, I wanted to show you, to illustrate how this lemma can be used. And now I'm coming back to the graph again. So we know that lambda 1 is less than lambda 2 if and only if the graph is connected for bubbles. And we also know that if this gap is big if and only if it's an extended graph. Now what happens if the next gap is big? Well, by van der Waals we know that in this case the eigenvector is essentially unique. And that just because that means that lambda 2 has multiplicity 1, because the eigenvector is unique, so we can forget about this condition on minimal support. And what it means is that so the positive and negative supports span connected graphs. So this suggests that maybe if there is a bigger gap there, then these graphs will have will be more than connected. And indeed, so the question is, does it, for example, imply that the positive and negative support are expanders? So suppose that the gap, there is a gap, does it imply that the positive and negative supports are expanders? Well, it obviously does not. So think of a situation where you have 2 graphs. I'm sorry, when did I start? So let's look at first just the disjoint union of two expanders. Of course, the 0 here has multiplicity 2 because it's disconnected, and there will be two eigenvectors belonging to it. I mean, many pairs, but one will be the all 1 vector, as always, and the other one will be all 1 on here and all minus 1 on the other. The third eigenvalue will, however, have a gap because it must cut either this or that into two sizable parts. Now let's add a very thin, say just a path connecting the two guys. Then this doesn't change the picture too much. So it will still be true that there is a substantial gap between the second and third eigenvalues. But if you look at the positive support of, say, the second eigenvector, which will be essentially almost 1 here, almost minus 1 on the other, and it splits this path into two parts somehow. So the positive support will consist of this expander plus a little tail, which says it's not an expander. But if you use the coordinates of the second eigenvector squared as weights, you get a weighted version of the expansion, which I leave you to define. It's easy to define what it should mean. And in that case, the above integration. So you do get that these are expanders. And well, it can be extended to lambda k and lambda k plus 1 for any k, which I think gives a nice combination of the Holland-Millman result with van der Waals lemma or the Noga theorem. The question is, there are lots of questions. I don't know if there is any reasonable reverse implication here, which I think would correspond to Noga's theorem. And I don't know if there is any other way of extending this notion of an expander. So somehow, what would correspond to these results of Cohen-de-Verdier that if the eigenvalue has large multiplicity, then the graph is planar. So that also is something which, in other words, if it has large multiplicity, the graph is not planar. So it also means that the graph is rich in some sense, and I don't know how to go on, whether both parts are non-planar or one of them is non-planar. It says something about being able to cut the graph into two non-planar parts and so on. So this is it's about the eigenvalue gap. Now, here are a couple of more related facts. So if a graph is tree-connected, then you take this matrix, Cohen-de-Verdier, this really good matrix that has a three-dimensional null space. It's a representation of the graph in free space. You can, if you want to, you can scale them to unit vectors. It gives an embedding of the vertices on the sphere. You can also include the axes arcs of the large circles. And then it can be proved that this is actually a planar embedding of the graph. So not only we know the graph is planar, but actually this matrix gives us an embedding of the plane. And even more, you can scale them differently. If you don't scale them to unit vectors, it's a little more tricky scaling, then actually it will give a convex polygon in C-space. So this matrix gives you a representation of the graph, it's a three-connected planar graph, as the skeleton of the convex polygon. We know that all three-connected planar graphs, Chinese theorem, can be represented like that. This is one explicit construction. In fact, it turns out that these matrices, these really good matrices are somehow in one-to-one correspondence with these representations of the graph, of the skeleton of the graph as a convex polygon, not quite one-to-one up to scaling, some kind of technical issue there, but they are essentially in one-to-one correspondence, because we have seen that you can go also back. If you have a convex polygon, we constructed a really good matrix from that convex polygon, and that is sort of the reverse. So these are these nice properties of this number. Let's go on and look at the next case. So with Lex we proved many years ago that this is at most 4 if and only if the graph is linklessly embeddable in free space. So the graph can be embedded in free space so that no 2 cycles of it are there. This is a very interesting class of graphs which I will not be able to say more about, except for one question which is unsolved, and I think it's a very interesting question. So if a graph is a path, then the null space representation actually gives an embedding of it in R1. So you just lay the path on the line. If the graph is too connected and outer planar, then the null space representation of any really good matrix gives an embedding of it in an outer planar way. And if it's C-connected planar, then the null space representation gives an embedding it in the plane, and also a representation as a convex polygon, a Chinese representation. So it is, well, some technical condition, but so the real question is suppose it's 4 connected and suppose it's linklessly embeddable. So is it true that this null space representation gives a linkless embedding of it? Well, it goes into 4 space, but if you scale it to the 3 sphere, then you basically get an embedding in R3, and we believe it's linkless. And if I have a couple of more minutes, I would like to talk a little bit about an attempt which was formed to try to prove this in a constructive way. This is interesting because it's really not trivial how to embed a graph, even if it's embeddable linklessly, how to embed the graph. Even to check whether a given embedding is linkless is a hard problem which is solved by van der Waals as a very nice algorithm to check that, but it's a difficult question. So the question is the following. We know that these really good matrices exist, but in some cases, how to construct them? So here is one example of this kind of algorithmic question. Suppose we have a 2-connected graph G. 2-connected only rules out some complications I don't want to deal with. And we would like to find what? Either an embedding of it in the plane, in an outer planar way, or we would like to find a really good G matrix with 4x3, which then would give an embedding on higher dimensional space. Now, of course, this is just one step in a possible construction by induction. It turns out that the proof that such a really good G matrix exists is not really constructive. It involves n consecutive uses of the implicit functions theorem in n dimensions, and the errors, the numbers are squared in each step, at least the way I see it, so they will become doubly exponentially small. So it's a construction which it's not really a construction. It's not really a constructive proof. So we set out to try to find a constructive proof of this fact. Now, let me remark that though this is not completely uninteresting, because as a special case, if you apply this to a C-connected planar graph, then it actually gives you a really good G matrix with corank 3 that gives you a representation in 3 dimensions. And from earlier results, we know that this representation is automatically a convex polytope. So this does construct a convex polytope representation, which is not, I mean, there are other algorithms, but it's a not straightforward question how to construct a Chinese representation of the gravity. Well, I will, okay, so I'll skip this and I will only, show you this, maybe just a very rough idea of the proof. So we start with a really good G matrix with corank 2, and then we take this defines a null space representation in 2 dimensions. Now, if it's an embedding as an outer plane graph, then we are done. Otherwise, then we will find some crossing between the edges there. And then we start moving the origin. In other words, I mean, actually we are shifting the whole picture in the other direction. So we are modifying the use, and then there is an explicit way how the entities of the matrix n change. And so eventually we move the use all the way to the origin, all the way to this crossing point. It turns out that as you move it, as long as the matrix changes continuously, you will not, I mean, you will always maintain that it has exactly one negative eigenvalue, unless at some point you start creating 2 negative eigenvalues, but at the point where it starts to happen, you will have 3 zeros, because the eigenvalues move continuously. So if one of them moves down to the negative half, then you will get 3 zeros, and then you stop and you're happy. You get 3 zeros and 1 negative. And of course, as you expect, the difficult point is that it crosses an edge. Then you have to work hard to see that it's how to do, because that's a discontinuity in the thing, but you can do it. And so altogether is just a sketch of this idea. And so let me thank for the attention and wish many more.